Hey, welcome to this another video of Cortex M3 resistors. Reference for this video is the definitive guide to ARM Cortex M3 second edition, page number 25 to 32. Contents of this video are registers and special registers. So let's begin with the temporary registers first. As we have seen in Cortex M3 processor, it has register R0 to R15 and a number of special registers. This R0 to R12 are general purpose registers, but some of the 16-bit thumb instructions can access only R0 to R7, that is low registers, whereas 32-bit instructions can access all these registers. Special registers have predefined functions and can only be accessed by special register access instructions. So let's see first general purpose register R0 to R7. The R0 to R7 general purpose register are also called low registers. They can be accessed by all 16-bit thumb instructions and all 32-bit thumb 2 instructions. They are all 32-bit. The reset value is unpredictable. Next is general purpose registers R8 to R12. The R8 to R12 registers are also called high registers. They are accessible by all thumb 2 instructions but not by all 16-bit thumb instructions. These registers are 32-bit. The reset value is unpredictable. Next is stack pointer. R13 is a stack pointer SP. In the Cortex M3 processor, there are two stack pointers. This duality allows two separate stack memories to be set up. When using the register name R13, you can only access the current SP. The other one is inaccessible unless you use special instruction to move to special register from general purpose register, that is MSR, and move special register to general purpose register is MRS. The two stack pointers are as follows. That is main stack pointer MSP. This is default stack pointer. It is used by operating system kernel, exception handler, and all application code that require privileged access. Second is process stack pointer. This is used by base level application code. Here is one example of stack push and pop. Stack is memory usage model. It is simply a part of the system memory, and a pointer register inside the processor is used to make it work as first in last out buffer. The common use of stack is to save register content before some data processing and then restore those content from stack after processing stack is done. When doing push and pop operations, the pointer register, commonly called stack pointer, is adjusted automatically to prevent next stack operation from corrupting previous stack data. More details on stack pointers will be covered in next videos. It is not necessary to use both stack pointers. Simple application can rely purely on MSP. The stack pointers are for accessing stack memory processes such as push and pop. In Cortex M3, the instructions for accessing stack memory are push and pop. The access assembly language syntax is for push register, pop register. The Cortex M3 uses push descending stack arrangement in the stack memory operation. Therefore, the stack pointer decrement when new data is stored in the stack. Instead of using R13, you can use SP in your program code. It means the same thing. Inside program, both MSP and PSP can be called. However, you can access a particular one using special register instruction, that is MRS and MSR. The main stack pointer, also called SP main in ARM documentation, is the default stack pointer after power up. Next is link register. R14 is the link register. Inside the assembly code, you can write it as either R14 or LR, used to store return program counter when subroutine or function is called. For example, when you are using the branch and link BL instruction, the example of program is shown here. In the main program BL function, this will place a call function using branch with link instruction. Here the program counter will be equal to function and LR will be equal to the next instruction in main. So when the function 1 is called, the program code for function 1 will be executed, and then with BXLR the program execution will return to the main program. Despite the fact that bit 0 of the program counter is always 0 and the LR bit 0 is readable and writable, this is because in thumb instruction set, bit 0 is often used to indicate ARM thumb instruction state to allow the thumb to program for Cortex M3 to work with other ARM processor that support the thumb 2 technology. This least significant bit LSB is writable and readable. Next is program counter. R15 is the program counter. You can access it in assembler code by either R15 or PC. Because of pipeline nature of Cortex M3, when you read this register, you will find that the value is different than the location of executing instruction, normally by 4. Writing to PC will cause the branch because an instruction address must be half-word aligned. The LSB of the PC read value is always 0. However, the branching either by writing PC or using branch instruction, the LSB of target address should be set to 1. Next is spatial register. The spatial registers in the Cortex M3 processor includes 3 parts. One is program status register, second is interrupt masking register, third is control register. So, spatial registers can be accessed via MSR and MRS instruction. They do not have memory address. So let's begin with program status register. Program status registers are subdivided into 3 status registers. First is application program status register, abbreviated as APSR. Then interrupt program status register, that is IPSR, and then execution program status register, that is EPSR. The 3 PSRs can be accessed together or separately using the special register access instruction, that is MSR and MRS. When they are accessed as collective item, then name XPSR is used. You can read PSR using MRS instruction. You can also change APSR using MSR instruction, but EPSR and IPSR are read only. For example, mentioned here in red text. In the first instruction, MRS R0 APSR. So this will read the flag status into R0. So next is MRS R0 IPSR. This will move the content of IPSR in R0. Next is MRS R0 EPSR. This will move the content of EPSR into R0. And then next is MSR APSR, R0. This will write the content of R0 on APSR. Next is control word format for this program status register. So various bit fields are involved in this control register. The description is as follows. N stands for negative, Z stands for 0, C stands for carry or borrow, V stands for overflow, Q stands for sticky saturation flag, ICI/IT is interrupt continuable instruction bits, if then instruction status bits. Then T is thumb state, it is always 1. Trying to clear this bit will cause fault exception. Next is exception number. This indicates which exception the processor is handling. So if you compare this with current program status register CPSR in ARM7, you find that some bit fields that were used in ARM7 are gone. The mode M bit field is gone because Cortex M3 does not have operation mode as defined in ARM7. Thumb bit T is moved to bit 24. Interrupt status bits are replaced by the new interrupt mask register PRIMASK, which are separated from PSR. For comparison of CPSR in traditional ARM processor, next is interrupt masking registers. Here we have three registers: PRIMASK, fault mask and base pry. In PRIMASK, a bit 1, a 1 bit register, it is a single bit register. When this is set, it allows non-maskable interrupts, that is NMI, and the hard fault exceptions will be allowed. All other interrupts and exceptions are masked. The default value is 0, which means that no masking is set. Next is fault mask. It is again a single bit register. When this is set, it allows only the NMI and all other interrupts and fault handling exceptions are disabled. The default value is 0, which means that no masking is set. Next is base pry. It is 8-bit register. Depending on the bit width implemented for priority level, it defines the masking priority level. When this is set, this enables all the interrupts of the same or lower level. Higher priority interrupts can still be allowed. If this is set to 0, the masking function is disabled. The access of this PRIMASK, fault mask and base pry registers, number of functions are available in the device driver library provided by the microcontroller. Details of these core register access functions are covered in actually in the datasheet. A detailed introduction of Cortex microcontroller software is also covered in datasheet. So in assembly language, MRS and MSR instructions are used. For example, MRS R0 base pry, this will copy the content of base pry on R0 register. Next is MRS R0 PRIMASK, this will copy the content of PRIMASK on R0 register. Next is MRS R0 fault mask, copy the content of fault mask on R0. Next is MSR base pry, R0. This will copy the content of R0 into base pry. MSR PRIMASK R0, this will copy the content of R0 on PRIMASK. Next is MSR fault mask, R0. This will copy the content of R0 into fault mask. So this PRIMASK, fault mask and base pry register cannot be set in the user access level. Next is control register. The control register is used to define the privilege level and the stack pointer selection. This register has only 2 bits. Control 1. In the Cortex M3, control 1 bit is always 0 in handler mode. However, in thread mode or in base level, it can be either 0 or 1. So, this bit is writable only when the core is in a thread mode and in privileged. In the user state handler mode, writing to this bit is not allowed. Aside from writing to this register, another way to change this bit is to change the bit 2 of the LR when the exception is returned. This subject, okay. So control 0, next bit is control 0. The control 0 bit is writable only in a privileged state. Once it enters the user state, the only way to switch back to privilege is trigger an interrupt and change this to exception handler. To access the control registers in C, the following CMSIS function are available. So, thank you for watching this video.